Last time I made this little circuit that can take a binary coded decimal input and display the decimal digit. And what I think I'm going to do this time is try to replace the switches over here with a different chip that I think, if I understand it correctly, means that I should be able to just push a button and it'll increment the counter. And then I think it probably loops. I was looking at these earlier, and what I was going to use was this 0 to 9 preset decimal counter, since I thought that made sense. But then I just noticed this BCD 4-bit binary counter, so I'm not actually sure what the difference is between these two. The diagram on here seems to be seems to be identical. So I'm not actually sure what the difference is there. I know that my chip here it takes BCD input, so maybe I should use this one. Well, I suppose staring at these isn't going to tell me the difference, so I should maybe look them both up. Okay, so the first one I'm looking up is this one here, BCD 4-bit binary counter SN74LS160N. It says it's a synchronous decade counter, direct clear, so it counts 0 to 9. I guess that's a decade counter. I don't know what I'm looking for here exactly. We have the different pins. I guess I should look up, I'll bring up the other one too. The other one was this SN74LS162N, which it says on here, it says it's a 0 to 9 preset decimal counter. On the data sheet, it says it's a synchronous preset decimal counter, 0 to 9 count. I mean, it seems like the feature list here is the same. So I don't know what the difference is between these. The pinout seems to be the same too. So I don't understand what the difference is between these. Why do they have different part numbers? It actually looks like this block diagram is identical too, so I guess I can use either one. Okay, I have no idea what the difference is between these. They seem to be the same. I'll just use this 160N. Here's the SN74LS160N. Okay, I have the chip. I think the first thing to do is hook up power to it using the pinout. Okay, and the pinout on this shows that ground is on pin 8, which should be this one, and VCC is on 16, so it's on the upper side there. Boop, boop. Okay, the chip should have power. I think I'll just hook the output pins up directly to this chip, and I'll get rid of this. And I don't know if it'll default to 0 or what, but I suppose that might be a first step. I can do that, turn it on, and just see what happens. So I think that's what I'll do. All right, that means I don't need any of these resistors anymore. Actually, it means I don't need any of these wires that went over there at all. Okay, I removed that switch and the resistors and those wires. So now I'm going to have to, because I don't remember the pinout, I'm going to have to look up this datasheet again for this this display driver. Okay, we have the datasheet for the 7-segment decoder driver here, and the pinout for the, let's see, A is pin 7 on this chip, and we want to do the outputs on this side. So A is 14 on that side. So I need to hook 14 to 7. This one to there. Okay, I'm hoping I have this hooked up correctly. I have the wires running from the outputs of this side to the inputs of this side. And then there's 3 that are unconnected I talked about in the last video. I still don't quite know what they do. I'm just going to leave them disconnected for now. Now, I'm not sure what happens here if I turn this on. I don't know if anything will occur, if this like defaults to 0 or random numbers, or if I have to hook up some other pins here to get it to work. But let's just try it. Okay, we're seeing possibly an 8, or possibly something is horribly wrong. Oh, look at that. I had a suspicion it might be somewhat random. Okay, I'm not sure. It's nothing now, but that's interesting. It was different the first time, and now it's just showing zeros. So probably there's essentially just random state in here. And when I first turned it on, it locked into that, I guess. And now it's locking into 0 for whatever reason. I think what I'll do is I will see if I can pulse the clock, and we'll just see if anything happens, right? And I think that works. Let me check the data sheet. So the clock is on pin 2. I think that means that when it gets a pulse, either like a high or a low, it's supposed to go to the next state. I don't know if I have to do anything else. Like, I'm not sure what enable T is, for example, or enable P. There's probably something that goes high or low to set these data inputs, which I'm assuming would be setting your initial value, perhaps. But we'll just try this now. So I think I'll just use a jumper. We'll turn it on. Oh, look at that, went back to 8. Okay, so if the clock's on pin 2 and I pulse it high. Okay, nothing happened. Low. There we go. Okay, it's working, but I suspect that it's picking up like bounce, right? Because it's operating far faster than I can operate. I can't carefully put this in quickly enough to get just one pulse because it's vibrating around in the socket. I think that's what's going on there. That makes me suspect that my idea of putting a push button on this might not work because I think pretty much all switches have some amount of bounce. I'm not sure. I'm going to try putting a switch in and we'll see how that goes. Okay, it does seem to be working. The first couple of presses, yeah, it did that. I'm not sure what's going on with that. Maybe something is clearing or resetting. Wait, so if I hold it down and release it, if I hold it down for a moment and release it, it seems to work far better. If I click it quickly, something horribly wrong happens. Maybe that's still bounce somehow. Or it could be because I don't have these other pins hooked up to anything. One of these is a reset or a clear, and I wonder if that is causing it. So maybe I should tie that to ground or something like that. Let's check the data sheet. Clear has a line over the top, which I think means active low. So I think that means that when it's low, it does its job. So clear is on pin 1. So if I tie this to low, yeah, it's always clearing. So we'll tie it to high. It should never be clearing. Oh, that works. That works quite a bit better. Okay. So the problem probably was this was floating somehow and it was sometimes clearing, right? So I'll just tie that directly to high so that we don't have that problem. Okay, so now it's never clearing. Okay, except sometimes it does, unless it's bouncing. And it's possible that when the switch bounces, it bounces so quickly that it just jumps, several digits and wraps around. But it does seem to be working. There, that's really cool. All right, if I turn it off and then back on, what happens? It happened to reset to 0, but I bet that's not guaranteed. I don't know, maybe it is. Let's see if the datasheet says anything about that. The clear function is asynchronous and a low level at the chip input sets all 4 of the flip-flop outputs. I don't think that has anything to do with the power on behavior. I think what that means is you can trigger clear at any time. It doesn't care about the clock's current state, I think. Both count enable pins must be high. I wonder if that's happening by accident. It says P and T must be high to count. Probably that's just happening by accident here because I didn't tie those to anything. So that probably means I should tie pin 7 and pin 10 high to make it more reliable, perhaps? Probably should have had the power off when I was doing that. Okay, I can't tell if it's more reliable, but my understanding of the data sheet would suggest that they should be high when you want counting. So I think that means this is how it should be wired up for my purposes here. So what are the other pins? We have a ripple carry output. And since that's an output, I don't think I need to worry about that one. I think what that is if you want to ripple, when this rolls over to go into like another chip or to know when it rolls over, right? I'm pretty sure that's what that means. I don't need that. So I've hooked up clear. We're using clock, although clock doesn't have a pull down or a pull up on it. So maybe I should do that. We have inputs. They're left floating because I'm not using them, because at least currently it's starting at 0. But I bet, okay, so, well, okay, there's load that's active low. I mean, I'm assuming you could assign anything to these, but I think I will tie them low. I don't know if it reads from those when the chip first turns on or not. I don't know if things work that way. Maybe not. Okay, the inputs are on 3, 4, 5, and 6. Pin 1 is clear, right? And we have it held high now so that it never clears. What does clear mean? Does clear return it to 0, or does it return it to whatever's on this initial input? I suspect you have to trigger load to read from the inputs. I don't know. I'm going to finish hooking up the inputs to 0 here first. I really got to stop doing this when it's turned on. Okay, all the inputs are tied to low. So if it ever reads from the inputs, it should be reading a binary 0, I think. I don't know if it reads it when it first starts up, though. I think what I'm going to do is I'm going to take this out, and I'm going to put in a jumper so we can do a little testing with it. So let's give it a number. Okay, so we'll hold it high first. That means it's not clearing. Okay, so we get to like 4. And then if we put it low, it resets it to 0. Okay, so the question, I guess, is it resetting it always to 0, or is it resetting it to what's initially loaded here? So I think I'll take this and I'll move this to be tied high, and we should see a different number if that's the case. Okay, nope. So it appears that clear is always clearing it to 0. So these only matter when you use that load signal. Well, I think I'll put a jumper on the load signal. The load pin is pin 9, and it says it's active low. So if I tie this to high, then that would be the equivalent of never calling load, right? And clear is active low, so I don't want it to be cleared all the time, so I will tie it to high. So right now we should be in normal counting behavior, which we are, with some bounce. Now, on load, this input, which I think this is A, is tied high, so that means that we're feeding the input by default has a hard-coded or hardwired 1000 on it. So I think it's hard-coded to 1. So if we then say load it, nothing happened. But I think you're supposed to do that on a pulse. Yes. So now it reset to 1 because we told it to load on the next clock cycle. Whereas this can be reset at any time. We can reset it by going low on the reset signal. Okay, I think I mostly get this then. So the idea is that on a clock pulse, it does stuff. The only one that really seems to be the exception to the rule is this one here, which is the clear, because clear is specifically asynchronous. So you can clear it at any time, regardless of what the clock is doing. But the clock drives this. So when load is tied low, because it's active low, the next time it gets a clock pulse, and it appears to be on the rising edge, because I'm holding it down now, when I release, it does its action, right? When the signal goes from low to high is when it does its action. So what it did is because the load pin had a low on it, it didn't count. Instead, it loads from the inputs. But when this is high, which is the equivalent of being off because that's an active low signal, now it's in count mode. And those other enable pins that I tied to, I think high, yeah, I think this was one and this was one, I think are enable pins. I'm not sure why there's 2 of them, but I'm guessing maybe one, well, how about I just look? Okay, because there's enable P and there's enable T. Up here it calls them both count enable inputs, and they both have to be high to count. Input T is fed forward to enable the ripple carry output. So maybe when T is low, there's no ripple. And that's the only distinction between the 2 of them, but they both have to be high for it to work. I could probably reason it out by looking at this or trying to decipher this block diagram. Let's see, P and T are here. P goes into, I guess, a big AND gate here, like a three-way AND gate. At least, yeah, I'm pretty sure that's an AND gate. And then T also goes into that same AND gate, but T also goes way down here to an AND gate that gets to ripple carry out. So, okay, so that matches what the text said. If T is low, if it's false, this gate will be off. And this gate will, of course, be off. So no counting is going to occur, though, because this gate seems to go into... Well, I'm not sure. Okay, tracing through that logic is definitely tricky, but so it branches off here and it goes to all these other gates. Okay, it seems like, just from a quick glance, it's ANDed into all of the inputs. So yeah, unless P is high, you can't read anything from any of these inputs. I think that makes sense. So then T, though, like why are P and T separate? So I think it won't count, possibly won't even load if P is low. So when load is active, counting is also disabled. I think that's what I'm seeing. I'm having a hard time tracing through this and keeping a track in my head right now, but I think that's the case. Okay, so the question, my initial question was, why have P and T why have them be separate in the first place? I think it means that when P is off, all of the inputs are ignored. I think counting is ignored. Yeah, I'm not entirely sure why P and T need to be separated, but I think that's why they're separated, so that you can essentially disable all of the counting features, but still read whether or not you've looped. Well, actually, I suppose all of the outputs are probably always active, right? They always are showing whatever their last state was. Okay, well, regardless of if I fully understand the data sheet, this is pretty neat. I actually expected the bounce to be worse than it was. Obviously, if I tap quickly, it skips past. But as long as I'm pretty intentional about pushing down, and I suppose that's because the clock is active on the rising edge, I guess. So it has less opportunity to bounce probably when I just lift my finger, because the springs in these switches they're pretty tight. So I'm assuming that is preventing it from bouncing when it releases. So that makes it for a pretty clean signal. On down, I suspect it bounces quite a bit because I am unable to perfectly push it down. Okay, so the only other thing that I'm not sure about is when I'm pulsing the clock, it's disconnected from anything right now. So essentially it's floating right now. So I wonder if, should I have a pull-up resistor on the clock? I don't know if it would actually help or if I would notice anything, but I suppose I should do that. So let me dig out a 10K. Okay, I have a 10K now on the clock, pulling it up. And then my switch is connected here, which pulls it straight down to ground, but only when I'm pushing it. I don't really know if I'm going to be able to tell any difference because... But I suspect that this is probably more correct, like when using a push button, because you don't really want it to be floating. You want to have consistent behavior. So I assume that that's probably better. Okay, so we reset to 8. Let's reset it to 0. Okay, and count. Oop. Not sure what happened there. I wonder if this wire moved, maybe? 1. Ooh. It actually almost seems like it's made the bouncing worse. No, we're skipping 4 for some reason. Huh. Okay, so maybe there's a possibility that it did make the bouncing worse because it's pulling it directly to high, like as soon as possible. Maybe that makes it more sensitive to tiny little minute vibrations in the switch when it springs up. I don't know. In my head, that kind of makes sense, but I can't explain it, and I don't know if that's correct. Obviously, I should have some kind of a debounce in here, I suppose, and I'm not sure what that looks like. All right, this is really cool. I got a counter going, and next time maybe I'll try to get some kind of a timer going so that it counts automatically. I don't know. That might be fun. Anyway, if you like it, give it a thumbs up or subscribe if you haven't, and see you next time. Bye.